we started talking about harmonic motion last time. Harmonic motion, oscillatory motion, vibrations, those are all ways of saying the same thing. It's just saying things are going back and forth in some way. We're talking about vibrations, harmonic motion, mostly as a lead into waves, because waves are going to be an important thing. We've so far talked about the fact that, harmonic motion can be complicated. For example, the top of a fancy 300-year-old violin, if you tracked the motion of the wood on the top of a violin, it would have this, calculating mathematically how it vibrated would be complicated. And that's what gives it an interesting sound. If it wasn't a complicated motion, it wouldn't, it would sound like a Casio keyboard or something. So that's a harmonic motion, but it's a complicated harmonic motion. We're not dealing with those. We're only dealing with simple harmonic motion, it's called. And that's harmonic motion where particles follow this formula. So simple harmonic motion, the position as a function of time is equal to A times the cosine of omega t. And if this simple harmonic motion is a spring mass system, then you can also calculate this constant omega in terms of the spring constant and the mass. So if you have a spring mass system, then omega is equal to the square root of k over m. And then we talked about how this omega value, anyone remember what the name for that variable is? Close, angular frequency. Yep. And that is equivalent information to the period. And it's also both of those are equivalent information to the frequency. So if you know any one of those, you can calculate the other two. What we haven't talked about yet is the speed of an object at points in its path. So I'm just going to give you two formulas for that and give you a couple things to keep in mind as you do this, and then I'll do one or two example problems. Is that right? No, then I'm going to go on to just extending this spring mass system a little bit. So what's the fastest that an object can go when it's, so if you have a mass on a spring and it's vibrating back and forth, what's the fastest it can go? Well, what are some things that you think would affect how fast it goes to this fastest point? That would, but we're ignoring friction in all of these. If you're going to pull it out to a certain distance, say you're going to pull it out 10 centimeters and let it go, the stronger the spring is, the faster it'll get going, right? That makes sense intuitively. And maybe not quite as obvious, but this is also true. The less mass the thing has, the faster it's going to get going because it's easier to accelerate. The spring's applying a force to something with less mass. So K and M both affect how fast it goes. And in that sense, let me say K and M both affect the max speed. So it makes sense that omega would would affect the maximum speed because omega takes both of those into account. That's just sort of a good way to, I think, wrap your head around the connection to omega. And then the other thing is the maximum speed. Do you think it would be bigger if you pull the object farther from its resting length or pull it less far? Farther, yep. So the amplitude affects Vmax also. And so the formula says Vmax is equal to the amplitude times omega. And in the object's motion, where would you guess the mass reaches its fastest speed? Where in the path? Well, think there are probably three likely candidates: the resting position right in the middle, or the two endpoints. So think about what this motion would be like, and think about which of those is going to most likely be the fastest. Okay, so the endpoint, and both of the two endpoints, this is true. That's where it's changing from going one direction to the other. So it has to be slowing, as long as it's some kind of smooth motion. It needs to be slowing down, stop for a second, and then start going the other way. So that's actually, the speed is 0 at the two endpoints. So the fastest it ever goes is right in the middle. And you can think of it as the spring is pulling it back, so it's speeding it up until it gets to that resting length. As soon as it gets to that resting length, it starts pushing to try to stop it. So it's speeding it up until the resting length, and then it's slowing it down after that. So this occurs at the spring's resting length. And another way to say that, what's the p-value at the resting length? 4 pi? No. 0, right. So we just always choose our 0 position to be at the spring's resting length. So p equals 0 always represents that. Okay, and then besides calculating the maximum speed, we can also calculate the speed at any given position. So the speed at some chosen position p is given, so I'm going to write this as the speed is a function of p, so the variable is p, is equal to some fraction of Vmax. Okay, so I'm going to multiply this by something that is somewhere between 0 and 1. Okay, and it's multiplied by 1 minus p squared over a squared, and all that square root. Okay, so let's just plug 3 values in here to make sense out of this. Okay, so think about so here's the mass at the spring's resting length. Here's the mass when the position is negative a. So that's at the extreme edge on that side. And here's the mass when p is equal to positive a. Okay. So what are the values of the speed at these 3 points? P equals negative A, P equals A, and P equals 0. Well, at P equals 0, what do we expect this formula to give us? We expect it to give us V max back, okay, because that's where that maximum speed occurs. So plug 0 in for P. You get 1 minus 0, so you get 1 inside the square root. Square root of 1 is 1. And so V of 0 is equal to V max. Okay, so that works. Yay. So now how about P equals negative A? So the speed at negative A is V max times 1 minus negative A squared over A squared, square root. Negative A squared is the same as A squared. So this gives you 1 minus 1. So you got the square root of 0. And so 0 times V max is 0. Okay? That's the point where it's turning around. So this makes sense. Okay? And then the last one, when P is equal to positive A, then you have V max. It comes out to be 0 for essentially, the same reason. You just have 1 minus A squared over A squared. A squared over A squared is 1. 1 minus 1 is 0. And this gives 0. So that makes sense. So this formula makes sense for the 3 points that matter the most to us. The infinitely many other points we're just going to have to trust. But actually, anybody have any idea, think back to last semester, what technique you would use to prove this formula? We could go through it. I'm not going to because it just takes time and whatever, but like we did a topic that would pretty easily, quickly let us calculate this. Well, here's a hint. What? Well, you could do it that way, but we didn't talk about it that way. But we only had one topic where we talked about springs. Yeah, conservation of energy. So if you use conservation of energy, remember that always relates a change in position to a speed. Remember that formula? And so that's the way to do this. So if you guys want to do this on your own, that's where to go. I'm not going to. Well, because I know, because here's what would happen if I started doing it. You'd be like, oh, good, I don't have to listen for 8 minutes or whatever. And then you just like hum the song to like the Betty Crocker commercial in your head while I did this. Any questions about that?
So when it's at position 0, which is the resting position,
yes.
The velocity is 0?
No, the velocity is V max. Well, the speed is V max at the resting position. Oh, okay. Well,
V times 0 equals V max?
This one gives you V max times 1 because position at the resting length is equal to 0. So you have 1 minus 0. And so you end up with 1 times V max. And so you get V max when it passes through that resting length.
Right,
Okay, so here are a few things to think about with what we've talked about so far. Like, these are good things to just keep in mind. First of all, there's one equation, and that is F equals 1 over the period, that is true for any harmonic motion, including the complicated motion of a violin top, okay? So this is true for any harmonic motion. All the other equations are only true for simple harmonic motion. Second, if you're talking about a mass spring system, you can use the fact that omega is equal to square root of k over m. If you're talking about any other type of simple harmonic motion, you need to find that omega value another way. You know, essentially, that one is kind of common sense when you think about the fact that k doesn't mean anything if you don't have a spring in your system, you know. Okay, so for other simple harmonic motion, you need to find omega another way. What if you're not talking about simple harmonic motion? What if you're talking about some general complicated harmonic motion? Then how do you find omega? It's a trick question. There's no such thing as omega except for simple harmonic motion. So this only matters to us because of that cosine formula that represents simple harmonic motion. Okay. And third, to use this formula, P of t is equal to A cosine omega t. Requires that the position is equal to A when time equals 0. That's just mathematically, that's a requirement for that cosine function. So what if, say, in measuring your motions, the stopwatch is clicked on, you know, turned on when time is not equal, when position is not equal to positive A. You know, what happens? Well, think of it this way. The motion follows this pattern no matter when your time equals 0 is, okay? This is a property of the motion. When time equals 0 occurs, just determines where the y-axis falls. So if you click on your stopwatch when the position is equal to A, you get this, and that's a cosine function. If you click on it over here instead, it's not a cosine function, but fundamentally the motion's still the same. And so if you are dealing with a case where time is equal to 0, where this green line is, there's some mathematical fiddling you have to do to make it work, but all of the properties of the motion are still the same. And that's why we're just not going there, you know, like we're going to assume that position equals A at time equals 0 every time, because we just don't gain any more physical insight by dealing with other cases. Okay, so we're just glossing over that. Okay. Any questions about that? Yep.
When you wrote that part that said, what if, say, stop opposite job, that, the wraparound where it says P equals A, should that say P does not equal A? Like you said,
Yes. Yes, yes, yes. Thank you.
still type A wrong.
Yes, thank you.
Verified.
Yeah. No, that would totally, everyone would go back to their notes later and that would, yeah. Any other questions? All right. So now here's a question for you. So if you have a spring mass system, like this, where the spring constant is K and the mass is M, this thing is going to oscillate according to this function, right? And we know that omega is equal to square root of K over M. And we know that we can calculate the period this way, right? So we can figure out everything about the motion. What would you guess? So what if now you took that same spring and that same mass and hung it from the ceiling and got it oscillating again? Do you think, so would the frequency, would it start to oscillate faster, or would it oscillate slower, or would it oscillate the same? Just think intuitively about that for a second.
Same.
That's right. Yep. And I think this is something that sort of surprises a lot of people. And more people than think the other way. More people think that like this is going to make the spring tighter and that's going to make it oscillate faster. I can sort of see how you would think that, but it turns out that that's not the way this works. Okay. So the oscillation frequency is exactly the same. In fact, we can still use all the equations that we've been using for this system when it's hanging vertically. In the vertical configuration. Just notice that P equals 0 now represents the spring's hanging equilibrium position. And that means, so if you imagine what would happen here, gravity is going to be pulling down on the mass, and that's going to mean the equilibrium position has the spring a little bit longer than it would be if it was vertical. right? So represents the hanging equilibrium position, and that means the spring is a little bit longer. Well, it could be a lot, could be a little, than in the horizontal equilibrium position. And the difference between the spring's equilibrium length horizontal versus vertical is mg over k. Okay, so let's think about the relationship between this formula and those variables and make sure this makes sense. So if the mass is bigger, would you expect the hanging length of the spring to be longer or shorter? Longer, right? That extra mass is going to pull it down farther. And if the spring is stiffer, would you expect the equilibrium to be longer or shorter than if the spring is flimsier? Shorter, right? The stiffer spring won't stretch as much. And so those are the relationships that you see with these variables. If m gets bigger, this whole formula gets a bigger value. If k gets bigger, this formula gets a smaller value. Okay. Yeah. K represents the stiffness of the spring. So a really thick steel spring has a big K value. A really thin, easily stretched spring has a low K value. Okay, so I think you can think of it this way. Imagine you have like a gravity switch. Then when there's no gravity, this distance is some unknown length L, right? Now switch on gravity. That mass will be pulled down. There'll be this distance L to get to where it was before, and then there'll be this extra distance mg over k that the mass hangs. Okay. Any questions about that? Okay. So I have a problem that I'd like you to work through together. Think about it, compare answers to each other, talk to each other if you get stuck. So say that a spring has a horizontal resting length of 0.15 meters and a K value of 100 newtons per meter. And say that there's a mass connected to the spring of 0.75 kilograms. So now the mass hangs vertically from this spring. It's hung vertically from the spring, okay? So you take this spring that's described here, hang the mass from it vertically, and from its vertical equilibrium position, the mass is lifted 0.1 meters and released. So that'll get it oscillating. So first, what's the frequency of the system? Second, what's the fastest speed that the mass reaches? Third, how far below the ceiling is the mass when it reaches that top speed? And then last, what's the farthest the mass gets from the ceiling? In doing parts C and D, I think it's a good idea to just sketch this out. If you can sketch what's going on, you're a long way toward answering those questions. Okay.